So good morning, everyone. Welcome to the session of Memory Design and Test course. So let's start with what we were doing in the last class. So what were we doing in the last class?
Service or different figure of merits, cell stability, right time, right margin.
Okay, we looked at various figures of merit of an SRAM cell. We started with which figure of merit did we look at first?
The cell current.
The cell current. What is cell current?
So the current, when we are reading from pass gate, the current is flowing from pass gate, then pass pull down network.
The read current, sir.
Read current.
It's basically the read
The
current.
read current of an SRAM cell. As we turn on the word line, there is some current that will flow from the bit line into the ground, into the source terminal. So pass gate to pull down path is what is coming into picture. Okay. What was the next figure of merit?
Line leakage.
Bit line
leakage.
Bit line leakage. And why is it important?
Sir, because what we logically think that one bit line is discharging and the other bit line in constant, but actually the other bit line is also discharging. So we need that time when the both bit line discharges, so that will trigger the sense amplifier.
So it limits the time of access time.
Okay. So one bit line is discharging because of the read operation, but the other bit line is discharging because of leakage happening on all the other unselected cells. And we need to consider that leakage also when we want to trigger the sense amplifier. So, okay. Then what was the next trigger of merit?
Cell stability.
Cell stability. Okay. So what is cell stability? What is the measure of cell stability?
SNM.
SNM. Okay. Something more? How do you? What are the methods of SNM that we looked at? Measuring SNM that we looked at.
So the noise injection we looked at, how much noise we can inject so that still we can preserve the internal memory states.
Okay. And what else?
The butterfly curve.
Yeah, we looked at the butterfly curve. So what is the noise margin in terms of a butterfly curve?
It is the largest square that can be fit inside the smallest lobe.
Why smallest lobe? Why are the two lobes not equal?
So the two lobes might not be equal when the sizing of the transistors are not the same. If it's not symmetric inverters.
If the two inverters are not exactly having the same transfer characteristics, that is, you have an asymmetric cell. In that case, one of the lobes will be bigger than the other lobe. And in that case, the smallest square that we can fit into the smaller lobe is what our noise margin is. Okay. And even if I design the devices to be same and symmetrical, inverters to be symmetrical, is there a possibility that the butterfly curve for a given memory cell can be asymmetrical?
So can it be due to the VT mismatch?
Yes, because of mismatch, it can always happen. Because of mismatch, some devices may have higher VT, some devices may have lower VT, and we could actually have imbalanced butterfly curve. So again, even in a symmetrical SRAM cell, when you run Monte Carlo, you will see that the lobes will not be matched. And then the biggest square you can fit into the smaller lobe is what your SNM is. Okay. So when you do your projects, you will be asked to design some memory cells. So I think many groups will take up a project on memory cell design. In that case, when you will have to measure the figure of merit for the SNM and other stuff, you have to ensure you are using the smaller lobe to measure your square. You are looking at the minimum noise. Okay. Okay. Then what was the next figure of merit?
Retention voltage.
Okay. Why is retention voltage important? Do you want it to be high or do you want it to be low?
Low.
It has to be low.
Why do you want it to be low?
To minimize leakage.
Because leakage reduces exponentially as you reduce the voltage of operation. In retention mode, you're not operating the memory cell. What is the status of the word line in retention mode?
So 0.
Word line is unselected.
Unselected.
Yeah. Okay. Then what was the next figure of merit?
Right margin.
Right margin. What were the two definitions of right margin that we looked at?
So one was with respect to the bit line, and one was respect to the word line. And word line, with respect to the bit line, it was the highest level of bit line.
Yeah. Now someone else will tell me about the word line.
It is the lowest level of the word line, which can allow a change in the cell content.
Okay. So for the bit line, we said it was the highest level of bit line at which we can write into the memory cell. For the word line, we said this is the lowest level of word line at which we can still write into the memory cell. What was the next figure of merit?
Right time.
Right time. Okay. What, like in a memory cell, which side will usually determine the right time, or may I actually end up determining the right time?
So the one,
the side where we store one.
Yeah, but not necessarily. Let me tell you, not necessarily. If the PMOS is strong enough, then one can be written very quickly. Only if the PMOS is very weak, that the PMOS will decide the right time. Okay, but yes, writing 1 and 0 both can happen. But what is important to realize is that first we write a 0. Only after a good 0 is written, not a very good, but a reasonably good 0 is written, will we be able to write a 1. So typically one can expect 1 to be the worst case. But if it so happens that my PMOS is strong, then 1 can actually be written before 0. So when you want to estimate the right time, you have to measure both 0 and 1 writing. You cannot just measure 1 writing. Okay.
So, but isn't it given that 1 will happen after only the 0? So
yeah, but look at it like this. I would start to call something 0, or my PMOS will start to turn on as soon as the node which was to go to 0 goes below VT of the PMOS.
yes, sir.
So it may happen that the PMOS turned on well enough and it charged 1 on the other side. Whereas the pass gate was so resistive that even though it had taken it below the VT of the PMOS early enough, it could not take it to full 0 by the time 1 was written.
So, but like we also came to the conclusion that the pull-up will be the weakest device of the technology.
But what happens in the presence of mismatch?
Okay.
You can't ignore mismatch when you talk of memory cells.
Right, sir, right.
Okay. So when you write your equations to measure the right time, for measuring it during the simulations, Monte Carlo simulations, you have to measure both and then take max of 2 of them. Okay. Then what was the figure of merit after that?
Leakage.
Okay. What is this leakage about? We already talked about one kind of leakage earlier. So what is this leakage? How is it different than that one? So why are only 3 people speaking? What is happening with others?
This is the overall leakage.
We are talking about overall leakage. Yeah.
Okay, we are talking about overall leakage. What does this depend on?
Junction leakage.
Size of
bit cell.
the transistors. Yeah.
Okay, junction leakage, which is directly dependent on the size of the source drain, so size of the transistors. Then
all of devices in the bit cell leakage.
All our devices leak, but on devices also leak. Junction
Yes,
leakage तो वहाँ भी हो रही है.
On का. Yes, sir.
So what do you do to reduce leakage of the off devices?
Pass gate.
Long channel.
Reduce the size of the transistors. Yeah.
So
First
small
of all,
PGPD PU. You can use it.
Yeah, that is anyways you want to do. Area के लिए भी वो better है. What do you do specifically for leakage?
Large length devices. You can use.
Large length devices. So we discussed that almost never do we use minimum length devices in the SRAM cell. Okay. What else could we do to reduce leakage?
so
Less
thick
doping.
gate oxide.
Less doping on source and drain.
Okay, change the doping on source and drain, which would change the VT. Okay. And
Gate oxide should be thick.
yes, to reduce the gate leakage, we could say that we would use thicker gate oxide. So we look at all the different components of leakage. We look at junction leakage. What do we need to do to reduce junction leakage? We said we would reduce the sizes of the devices. Then we looked at subthreshold leakage. We saw how to reduce the subthreshold leakage. We said we increase the length of the devices. Then we look at gate leakage, and what to do to reduce gate leakage. We say, okay, we can use thick gate oxide, and we could reduce gate leakage also there. Okay, so great. After that, we did a quick cell optimization analysis. What was that about? Which device is the biggest in a memory cell?
Pull down.
Pull down.
Sorry?
Pull down.
Pull down.
Pull down.
Pull
Yeah,
down.
pull down NMOS is the biggest device in the memory cell. Which is the smallest?
Pull up.
Pull up.
Pull up, the PMOS. And what happens about the pass gate? What is about the pass gate? What's the game there?
So PG is typically less than PD, pull down network.
Okay, but can I keep it very, very small?
No, sir.
Why?
Because
Yeah,
the read
pull up
access time would be impacted.
Access time would be larger, the cell current reduces.
Okay, the access time will go very bad. And will something happen to the write operation also?
सर बम्प एस्टिमेशन में दिक्कत होगी
इसमें?
Sir, small PG, so difficulty in write operation.
Yes, if the PG is very small, then write operation also becomes difficult. Okay, great. So any questions from the last class? So we just reviewed the last class and it's almost in its entirety. Any pending questions? Anything else that you are not able to understand and you want to ask something?
Sir, I had regarding the write margin. So, sir, when we were considering write margin, we talked in terms of the voltages, and we were considering the VGS and the VDS. So, sir, my question was, is it when I am talking about the highest level of the bit line or the lowest level of word line, is it by design I'm taking to that, or it happens and I somehow then try to resolve it by the sizing that?
Yeah, see, it can happen. I usually would not want to keep bit line at a level higher than ground, है ना? But due to RC, due to some extra mismatch or some variations, it can happen that my bit line does not really go to 0. I need to know what kind of margin do I have. Suppose I'm operating at a very low voltage, bit line goes to 0 very, very slowly. Then how fast will I be able to write? It will not just depend on the internal memory write time. It will also depend on what is the write margin there. It will also depend on the slope of the bit line fall. So many things.
Okay, so
we don't design word line to be low, but it can be low.
Okay, so I compensated by sizing the pass gate and the write driver to be.
No, you do not compensate it. You just plan for it.
Okay.
You would want word line to go to full VDD. You would want bit line to go to completely to ground. In fact, the next exercise that I had given you was about how to estimate Vx and how to estimate Vy, and you will see that we will arrive at write assist and read assist schemes, and we will see that going to negative bit line helps, going to voltage higher than regular word line voltage helps. We will look at these schemes to improve writability. We will look at schemes to improve stability. That is why this homework I had given to you. Have you guys started on that homework? Any questions on that?
Not right now, sir.
It's not a simple homework. It will take some time to solve it.
Yes, sir.
So better start. Okay. And on Monday, because on the next class, actually, I will not give you the detailing. I will simply go to what it is. I will give you the final equation. So if you're not done it, then you lost the opportunity. I do not want you to lose the opportunity of doing it yourself, because when you do it yourself, you learn better, you understand things better. So I want you to develop that understanding. That is why I'm suggesting that आप attempt करें उस homework को पहले. मैं तो आगे बढ़ ही जाऊंगा.
Yes, sir.
So what do we do today? Today we will look at the. Okay, but before going much further, we will let me update you about a few logistics. So we already agreed last time that our substitute class timing will be 4 to 5:20 p.m. on Wednesdays. Substitute means that if due to some reason I'm not able to conduct the class on either Tuesday or Thursday, then I will also tell you what time or which Wednesday I will be conducting the class. Okay. For out of class availability, my office hours will be on Wednesdays 1 to 2 p.m. Gagandeep will be available on Mondays from 6:30 to 7:30 p.m. and Bilal will be available on Saturdays 12 to 1 p.m. So we've tried to spread them out. So on almost on every day we are meeting in some way. Either there is a class or there is some office hour, so that we can support you with the course. Okay. We have only 2 TAs in this course, so we could not add much more, but we also have lesser assignments. So I believe you will need lesser support from TAs for the project you will need, and then we will see if we need to add more availability there. Okay. Any concerns? Are these timings okay? Office hour timings okay with all of you? Any one of you have a clash? Okay. So we will keep these office hours. And now we look into a bit cell layout.
Sir,
Yes.
can you explain on the butterfly curve how the noise margin there? The two noises should be equal, then only you are forming the square. Can you explain that?
Yeah. So we are saying that I inject 100 millivolts of noise on both sides. So that is where we are saying both sides we are injecting the same noise. If we're injecting the same noise, then we're talking about a square, not a rectangle. Am I right?
Yes, sir.
That's
so if noise is equal, then it will form square directly in the first step itself.
Yeah. So the biggest square we can put in the lobe, that is what is the noise margin.
Yeah. Okay, sir.
Okay. Ranjit?
Sir, I have a doubt with regards to this cell stability itself. Sir, when it comes to introducing the noise, is it that we are introducing the noise at the internal nodes, or is it on the bit lines?
No. So when we are talking of this noise injection, we are assuming that this noise is injected on the internal nodes. Okay.
Sir, in that case, if we are introducing the noise in the internal nodes, then there is the concept that we discussed on sizing the pass gate and the pull down, so that it has a potential divider configuration. So that doesn't come into picture on it, sir, because directly we are increasing the node voltage Vx.
Yeah. So noise is injected on the internal nodes, Ranjit.
Yes,
so Vx, we have to increase we add some noise.
Yes, sir.
During the read operation, this Vx automatically by default is not 0. So if when word line was not selected, I could inject a noise of 400 millivolts. If during the read operation, my base Vx instead of 0 is 250, then my noise margin is only 150. If I reduce my Vx to 100, then my noise margin is 300. That is why we need to keep the Vx low.
Okay. Still, I didn't get a better picture, sir. Maybe I'll just read on it more and I'll get back to you in the office.
Yeah, exactly.
Yeah, thank you, sir.
Yeah.
So similar, sir, in relation to this only, I had a doubt. So when the reading, we are consider Vx pump. So that Vx pump is basically intentional injection of noise before we start.
No. So Vx is not noise. Okay. Vx is the design.
Okay.
The Vx that I have asked you to calculate, the bump that I have asked you to calculate is the design.
Okay.
You can influence it. It is not noise yet. Noise is something that you are not able to control. And that is where the concept of noise margin comes in. That from the floor, from 0, I can inject a noise of up to 400 millivolts. Everything will be fine. The cell will not get corrupted. But as soon as word line goes on, my floor rises to 200. So now my margin is only 200 millivolts. I can only add 200 more millivolts there now.
Okay. So the site storing the 0 will in actuality will be storing kind of Vx kind of some that.
No, the site storing 0 will usually store a 0 only.
Okay.
But during the read operation, that 0 goes to Vx. Is that okay?
Okay, sir.
Okay. So now we come to bit cell layout. And some of you had seen this layout in the DVD course, but we will go in much more detail over here. So you can tell me which one of these devices is the, so what is this device? Is this pass gate, pull down, pull up? Which one is this?
It is the pass gate.
Pass gate, sir.
It is pass gate. Okay. What is this device?
Pull down.
Pull down.
Pull down. Okay. And we see that pass gate is smaller than pull down. So this is in line with what we had thought of. What about this one?
That is the pull down.
Okay. About this one?
Pass gate.
What about this one?
Pull up.
Pull up.
Pull up. So this is the envelope in which they are. Huh? What about this one?
Pull up.
That is also pull up.
Pull up, sir.
This is the pull up. And over here, I have also cartoon way में shown that pull up is still smaller than the pass gate. Where do you think is the word line?
Sir, it is at the pass gate poly.
It is at the pass gate poly. So in this particular cell, we will put some contacts. So what is this contact? This set of contacts?
Bit line.
Bit line.
They are the bit lines. They are the source node of the pass gate. Okay. What is this?
Sir, VDD.
VDD. Great. What about this one?
Sir, ground.
Ground. Great. What about this one?
Word line.
Word lines. Okay. So, and let me also put bit line over here. Okay. What is this one?
So VX.
What is the name of the node? Vx is the voltage we were talking about.
BLIT.
BLTI or BLFI, one of the two internal nodes. Now, this is also the same node. And do you see this is a long contact? Have you seen such a long contact anywhere else? All of you have made layouts. Have you seen a long contact elsewhere?
No, sir.
So what is happening here?
Sir, DRC rule follow नहीं हो रहा.
DRC rule follow नहीं हो रहा. क्यों नहीं कर रहे हम DRC rule को follow?
Sir, because memory है.
तो memory है तो क्या हुआ? What, why? So if it is memory, then we will not follow DRC. We follow so many DRCs in memory.
Contact where the area वाला DRC होता है ना, तो area वाला follow हो रहा होगा. इसे contact पे area वाला जो DRC होता है, वो वाला तो follow हो रहा होगा, मतलब इससे rectangular.
Is there an area DRC on contact?
नहीं sir. Distance between two contacts.
There is a DRC of distance between two contacts. So if I had not put this long contact over here, what do I need to do? I need to make a contact here and I need to make another contact here and then I need to connect them. Are you able to see this? And there is a DRC spacing between these two contacts that I have to maintain. That DRC spacing, maintaining that DRC spacing would mean I have to increase the height of the memory cell. This is what I don't want to do. And to avoid that, we use these long contacts. These long contacts are used only inside the SRAM cells, not even anywhere else in the SRAM, only in the SRAM cells. Why do you think only in the SRAM cells they allow this and nowhere else?
Sir, because of symmetry.
Symmetry.
Because we
I
want
can make
to,
my sense amplifiers also symmetrical. Many analog circuits I can make symmetrical. Symmetry, so I
to
can
keep
arrange.
it compact,
Sorry?
to keep it compact.
Yeah, so I would want to make my analog circuits also compact. Why not allow it there?
I think that because we have an array kind of structure, so we know the placings already. So we can maybe arrange them because we need to anyway design the whole to custom design. So we can do that by keeping the whole structure, the array structure keep in mind. So we know every split cell, so we can then any DRC we can by custom only we can take care of that.
So what we are saying is, what Raghav over here is telling us is that, see, in fact, this memory cell would always be there in form of an array. It is not just that I want to make this one contact somewhere or this one set of contacts in some region and then remaining area is completely out of my control. When we talk of an SRAM cell, at that point of time, I know that in this pura 1000 micron square of area, this kind of pattern would appear over and over again. Because this long contact helps us in saving area very, very significantly, the process teams say that, okay, because you are using an array, you are using a systematic formation of these long contacts, we will tweak our resolution enhancement algorithms, our optical proximity correction algorithms, so that such contacts can be formed fine in an array configuration. So you cannot use long contacts independently. Long contacts are allowed only in array configuration and therefore only in memory cells. Okay? Any questions?
So in case of standard cells, we didn't know which other cell will be abutted over the one we are designing. That is why we were not using that. And now in memory, we know.
Exactly.
Okay. Thank you.
Exactly.
So there is some kind of continuity in the memory, right?
I would not say continuity. Continuity you can have for standard cells also. That is not the thing. Repetition.
Yes.
Repetition would be the better word. Okay? Repetition and therefore a consistent pattern. Repetition leading to a pattern through which I could optimize stuff. That is all that we are talking about. Okay? So after we make these long contacts, what do? We add the metal stubs. So first we put the metal stubs on the boundaries, and then we make these connections of the BLTI, BLFI. Okay. Now again, notice we have done a DRC violation here, just so that I can maintain sufficient, spacing between the two metals. The contacts may not be fully covered. This again is not allowed elsewhere. Nowhere else in the design can you do this. Only inside the memory cell you may have such things. Even these notches that you have, the M1 notches that we have shown here, even these notches could be violating DRC. But all this is allowed simply because we want to gain density, and it is technically possible because this is a very repetitive structure extending over hundreds of thousands of microns. Okay, so we can do something about the optical proximity correction over there. If this was not that broad and that widely used symmetrical structure, one would not want to do it. It's much risky. Okay. So because we are doing all these DRC violations, do you realize that typically memory cell yield will be worse than other logic parts? We are violating DRCs here. Are you able to see this?
So what exactly is the notches for here? This notch thing?
Okay, if you do not put this notch, what happens? Your contact is still less covered, na? Ideally, you would want to cover the entire contact. That is what your DRC says, is it not?
Yes, sir.
We have not covered the entire contact.
Okay.
We are saying, instead of covering it fully, just put a small notch.
Extra
So that
metal. Okay.
it's not extra metal. It was the metal that was expected to cover the contact.
Okay.
You removed the metal from there. It is not extra metal.
Okay.
Can I ask something, sir? We are doing the DRC evaluation mainly because we want the density to be higher.
Yes, because area is diamond.
So, sir, we can do the DRC evaluations.
You cannot do. The technology team will do for you. So you will not really be designing these DRC evaluations yourself. Whichever company you join, unless you join a technology team there, unless you join the technology team that designs the memory cells, you will not be allowed to touch the layout of the memory cell at all. As a design team, you will be given this layout. But I'm preparing you for all kinds of job roles. So mostly, if you go into the design roles, you will only get a layout.
Sir,
And there are so many violations there.
So you also told we can technically do because it's a repetitive structure.
Yes. Technologically, this is enabled only because it is a repetitive structure. So we know what the neighborhood is. The neighborhood is not random. So then we put the VRs. Do you see there are so many structures that are shared across memory cells? We started with the contacts here. These contacts were shared. Now these VRs are shared across two memory cells, across the cell boundary. So these are shared across two memory cells. And you see this VR, for example, is shared across 4 memory cells. Do you see a paradigm shift? When we were designing standard cells, what did we say? That whatever is the cell boundary, leave half DRC from the boundary. Hana?
Yes, sir.
Over here, we are saying do the sharing. Again, simply because we know what the neighborhood is. We know that it is repetitive. It is the same cell that is going to come repeat there. But do you see that I will not be able to, when I'm saying it is the same cell that will repeat next, I cannot really place this cell exactly translated over here. I will have to mirror it such that this is how my design will appear. This will be metal 1. There will be a poly over here. There will be this poly would extend like this. You see, we are now mirroring the cell. This mirroring of the cell is called flipping. Is also called flipping. Mirroring to hai, it's also called flipping. So you do not translate the cell, you flip the cell. So the way it is referred to is like this cell, the original cell, let us say, is called as X configuration. When I mirror it, I call that as MX configuration, mirrored X. When I look at over here, the cell over here would be mirrored on the y-axis. So it would be called as MY. And then you mirror again and you will get Y. Okay. So you don't need to learn all this stuff or even remember all this. What I'm telling you is that when we abut memory cells, because we want to do sharing, we mirror the cells, we flip the cells so that we come into an array formation. We will just look at one of the array formations. So these are the bit lines, the word line stubs, the word line, and the ground connections. Okay. Now, do you see that in this particular layout, the word line that is running in the center has a lot of intra metal capacitance from the adjacent ground. So my word line capacitance increases very significantly. This is not what we like. So what we do is we actually cut the ground rails. And we say that we will overrun the memory cell with metal 4 rails, through which we will drop ground connections over here. Okay?
I'm not able to get this.
So in this slide, what do you see? You are getting ground from row decoder region. Are you able to see this? So see, this metal 3 that I'm going to run over it is connected to this node. This node is connected to the source of the pull down. This is ground. We just discussed that. है ना?
Yes, sir.
So we are getting ground from the row decoder region. But when I do that, what happens? There are two things. First is the word line capacitance increases. This is something I don't like. If the word line capacitance increases, it will rise slowly. It will also consume more power to select a word line and so on. So this is not to my liking.
So here we are talking about the Miller capacitance.
No, this is metal capacitance, intrametal capacitance.
So intermetal.
Intrametal.
Okay.
This is M3. This is also M3.
Okay. Yes.
There are 3 metal 3 lines running next to each other. There is going to be capacitance between them.
Yes, sir.
Hello?
Yes, sir.
So I don't like this capacitance. So what do we do? The only way to reduce this capacitance is cut the metal rail. But once you cut the metal rail, you still have to provide the ground connection. You provide that ground connection through a vertical metal 4 line. Instead of bringing ground from the row decoder region, you bring ground from, say IO region, vertically. Is that okay?
Yes, sir.
Similarly, you may, so over here, the VDD supply is provided in metal 2. Are you able to see this? So if you run metal 2 through the entire array, the VDD supply may see some resistance. To avoid that, you may also want to strap VDD supply, provide a metal 3 stub and a metal 4 connection somewhere at some interval, not every cell, but somewhere. Okay. So when you design the memory array, you have to take care of power routing of the memory array also very carefully. Okay. So if I just, as you're talking about putting cells in MX, MY and X, Y location, we get an array. Do you see this ground? This was the ground that is now shared with the adjacent cell. This is the word line that is shared across memory cells and so on. So we can make an array through which this sharing enables still higher density.
So from this, it seems that we have only done the kind of Y mirroring. We are mirroring vertically, right?
No, we mirrored along this axis and we mirrored along this axis also. They mirrored along both the axes. If I would not mirror along say this axis, then there will be a disconnect. I wanted to connect a bit line on the pass gate, and I need the bit line on. If I just translate it up there, there would be ground from here this side and bit line from this side.
Yes.
I cannot merge them. Therefore, mirroring on this side is also required.
Yes.
Okay. So, any questions?
I have one question.
Yeah, Yeah.
So when you were talking about the yield part, so if fabrication team is allowing us to violate some DRCs, so they have prepared masks for that layout. So why there will be a yield loss in such case?
See, if they could always, if the mask preparation and this optical proximity correction was so simple, Faisal, they would have allowed everyone to use the degraded DRCs.
Yes, sir.
They allowed only you because of the repetitiveness of the structure.
Yes, sir.
But it still meant that they are pushing the limits of the technology.
Okay, due to that pushing of technology, there may be the yield loss.
There will be yield loss.
There will be the yeah. Okay. Okay, sir. Understood.
So whenever a new process node is defined, let us say I want to define the 3 nanometer process node now. The yield is actually ramped up on SRAMs. SRAM yield is determined and measured, tracked to see how the process has evolved. Because SRAMs push the technology nodes, technology limits there.
Yes, sir. Yes, sir.
Okay.
Yes, sir. Understood.
Yeah. Anything else? Deepank, you had a question?
Sir, just confirming if metal 4 has not been shown here in this 2x2.
Yeah.
Okay.
Just because if I would show metal 4, you will not be able to see anything else. Already because of metal 3, I have put in some transparency on metal 3, but even then it's difficult to see what lies underneath. So that's why.
Sure. Thanks.
Yeah. Anything else? So in your projects, you will have to make layouts. So those of you who choose the SRAM cell project, you have to make the layouts and you have to ensure this kind of sharing is happening. Okay. In your course projects, you will not be allowed to violate DRCs, but you have to use this way of making layouts. Okay.
So we will be making this 2x2 or a single cell?
You will be making I will probably ask you to make a 64x64 array.
Okay.
Extract that. I will want you to make a 64x64 array, extract it, and then estimate the word line capacitance, bit line capacitance, etc. from that extraction.
Okay. Okay, sir.
So we will be using those long contacts, no, or we will
no. You will be doing DRC clean only.
Okay, sir.
You do not have the, what do you say, resourcefulness to design long contacts. Not allowed.
Yes, sir.
Okay.
तो फिर हमें सर हाइट बढ़ानी पड़ेगी.
हाँ, जो भी DRC क्लीन एरिया बनेगा वो मिलेगा.
ओके.
है ना? Okay. Any further questions on this? Great. So now let us look at some other layout topologies that were either used earlier or that you may see in some books, which are no longer used anywhere today. Okay. So this kind of a topology, they've already written where the pull-up is, and can you tell me where the pull-down is? Okay, that is also written there. Where is the pass gate? These are the pass gates. So this kind of layout was used, I think, more than 20-25 years back. But many books carry only this layout for you. That is why I had to make the whole layout evolution for you. Otherwise, I would not have needed to do it. Many books would show you only this kind of layout. But please, if you've done this course, do not ever make such layout in your interviews or anywhere. It is absolutely unacceptable today. Why do you think this layout is not acceptable today? Who can tell?
So lots of empty space and non-symmetrical a bit.
It is symmetrical.
They are using vias on each contact. So much vias.
We also use lots of vias and contacts. That was needed.
Maybe lots of turning.
Lots of bends. Really, look at this. This poly is bending. The direction of PMOS device and NMOS devices is different. There is a bend in the NMOS device itself. There are pull downs which are vertically, which are like this, and pass gate which is like this. Anyways, in advanced technologies, you want to keep things as simple as possible, not have any bends, nothing. So there are so many bends. यहाँ metal 1 का bend देखो, हर तरफ there are so many notches and bends. So this layout is nowhere used today, nowhere. Even if you now design in a technology which was 25 years old, you would want to use the new kind of layout that we discussed here, not this one. Okay. But yeah, over here also you will notice lots of sharing is happening. See, there's so many sharing happening here along this, because this is VDD line or ground line. So a lot of sharing happens over here also in these layouts, and you can actually make an array. But also you will see that many books, so this is taken from a book somewhere, you will see that the books have not again given you the concept of mirroring. Because they're not giving the concept of mirroring, you see they're not able to do the sharing across the cells. Are you able to see this? That was why in the beginning of the course I said no book will be able to actually give you what we are going to discuss in the class. Okay, so you will see all such stuff in the books. I'm not saying it is wrong. It is right, but it was right 25 years back. No one uses this today because this wastes enormous amount of area. Okay. However, in advanced technologies, for example, Hitachi and Renesas, they say that, see, in whatever we discussed till now, what did we say? We said that the beta ratio has to be greater than 1, so that my SNM is good. But in advanced technologies, because of optical proximity errors and corrections or whatever mismatch due to that, we see that using a regular layout, beta ratio equal to 1 actually meant a better yield. Look at this. These are the results. This is the 614, the bigger cell, which had beta ratio greater than 1. And this is the SNM. The worst case SNM is this. This is a cell with beta ratio equal to 1. Naturally, its median and mean SNM is going to be lesser than the cell with beta ratio greater than 1. Hai? Are you able to see this still here? Hello? If I would just give you these two cells, you know that the top cell has a better SNM than the lower cell.
Sir.
Yes. You have a question?
No, sir.
Okay. So since beta ratio of the top cell is better, we know that the median SNM is going to be better. And that is what we see also. But due to mismatches in manufacturing, do you realize that the worst case SNM of this array over here is worse than the worst case SNM of the denser array? The sigma is lesser.
Yes, sir.
And that makes a very, very big difference. That is why in memories, we or this is the standard to call as, this is called as a figure of merit. So you never say median or mean value of SNM. You never quote only SNM mean value or median value. Not just that, you always also quote mu by sigma. What would mu by sigma mean? It essentially, do you know what sigma is?
Standard deviation.
Standard deviation. Mu is mean. When I talk of mu by sigma, what I am essentially saying is that if it was a Gaussian distributed curve, then I will go 1 sigma away. There is some probability that I am covering, one set of cells I am covering. You go 2 sigmas away, I will cover another set of cells. 3 sigma away, I will cover another set of cells. So if my mu by sigma is very large, it means my variations are more controlled. My median is very high. I do not hit a zero until far away, until very many sigmas. So if you have to quickly estimate the mu by sigma of these two cells, which one has a better mu by sigma? What is the mu by sigma over here? Something like this. 6.4 hoga. Something, yeah. What about the mu by sigma over here?
Oh, 7.4 something.
7.4 something, sir.
Okay. So even though median value is lesser, we realize the sigma value is better, and that is why the worst case cell that you see in this region, the large cell fails. It is the small cell that is better. Not only did you save area, you also had better yield, finally.
So can you please focus on this mu by sigma significance? I'm not able to get exactly.
We will look at it in much more detail later, also when we talk about statistics linked to SRAMs. But abhi ke liye, we can look at it as the higher the mu by sigma, the farther away my mean is from zero.
Okay.
Not exactly in absolute terms, but in terms of sigma. So the small cell that is 7 sigma steps, 7.4 sigma steps away from zero, and the big cell is only 6.4 sigma steps away from zero.
Okay, and so that is more desirable the farther away it is.
Exactly, because that means that see, zero mein SNM zero ho gaya ek tarah se.
When it hits zero, okay.
And when it comes to zero, SNM becomes zero. So if I'm more sigma steps away from zero, it means more sigma cell is covered without getting SNM to zero. So what that means is I can have more cells. So suppose mu by sigma was 1. Then do you realize only this kind of cells were functional? Other cells would have sigma equal to 0.
Yes, yes.
But if mu by sigma was 2, then I add these into functional cells. If mu by sigma was 3, even these cells become functional. So greater the mu by sigma, higher the yield.
Okay. And so, for example, looking at both these curves, so we see that the worst case of lower is better. So since we are always characterizing based on the worst case, that's why we say that the lower one is better.
Yeah, because we look at what is mu by sigma. Because mu by sigma of the lower is better, we say lower is better. Okay. Is that okay? So
but still it's counterintuitive. I think it's not trivial.
Yeah, but it is important that you understand that not everything works according to your simplistic understanding.
Yes, sir.
Are you able to see that? That simplistically, yes. See, the mean value of sigma is 154 and 190. A simple person looking at it would say the blue cell is better. Is it not?
Yes, sir.
But a SRAM designer would ask the next question: what is the sigma? A standard cell designer would not ask the sigma. SRAM designer would ask what is the sigma. We were talking about it in a little while back also, that you cannot consider designing a memory cell without looking at mismatch. You will see many papers published by many students in different colleges Just do one simulation, no Monte Carlo, nothing. And they say, I have a very dense cell. I have this kind of a cell. People in industry would never even consider reading such papers. Unless you talk about the concept of mu by sigma, unless you talk about the concept of yield or anything, all the work that is done in academia is trash, not usable. Okay.
So if my mu by sigma improves, my yield is better. So in effect, I'm beneficial. Okay, sir. Yes, sir.
So with this, we move to the next part, which is other cells. We looked at 60 cells till now. This is other memory cell. What is the benefit of this memory cell? What is the benefit of this memory cell?
Sir, what is this RBL?
RWL. Let us say read word line.
Sir, the write and the read operations are separated.
The write and the read operations are separated. Okay, if I look at it as a single port cell, then you are absolutely right, Ranjit. I will write through word line and I will read through read word line.
Yes, sir.
When I've separated these write and read operations, what is the benefit I have drawn out of it?
It's cell stability, sir.
Yes. See, now earlier what was happening? When I was reading, there was a bump that would appear on BLTI or BLFI. So my read operation, my cell was very susceptible to failure. Now what has happened? I can read and there is no impact on the cell stability. Additional thing, I want to have a very high speed memory. If I would use the regular 60 cell, I would need to have a larger pass gate, which means I will need to have a larger pull down also, which means my area would anyways go up, including load on the bit lines would go up, everything. We saw it's a law of diminishing returns. Remember that? However, now I can size these two additional devices, the read port, independent of sizing of the pull down or independent of any other thing. So my read and write operations are decoupled over here. When I read, there is no noise that I inject onto the internal nodes. So my stability is better. Additionally, what do? Now, since read operation is not even of consequence, I simply size my write port according to the requirements of the write port. According to the requirements of the write operation. So I can actually make a more optimal cell, which is faster also and which is more stable also. Are you able to see this? Now, what happens if I use mux greater than 1 and I'm in a write cycle? What happens then? Does my stability remain high or there is something that happens then, which I do not want?
Sir, when you said that key in this cell, while reading, I will not be injecting any noise. So VX not there, sir. But why that I...
So while reading, you will turn on the RWL?
Yes, sir.
When RWL goes on, what happens to VX? Is it changing?
No, sir.
No, no. So there's no additional noise that is injected onto the system there. When will VX change? When word line is selected. But that is during write cycles only. So now my next question is, if mux is equal to 4 and I select my word line now, then there are 3 other cells in which I am not writing. In these 3 cells, I am not writing, but word line has gotten selected. What happens to the stability? Hello?
सर Vx थोड़ा सा चार्ज हो जाएगा.
Yeah, so it means that the cell in which I am writing, that is fine. वहां तो आपके पास पता है what data you want to write. But the other 3 cells which were also selected by the same word line, but you're not writing into them because the mux address is to select this one. These 3 cells are in the read mode only. And they have the same read condition as a regular 60 cell. What this means is that, in a sense, while you have decoupled read and write ports, the stability requirement still is similar. However, your read current can now be completely independently adjusted. So I cell now becomes independent of SNM constraint. If you were to use only mux1, then I would also say that stability problem is taken care of. But if I am not using mux1, I am using a higher mux, then stability problem remains. All that I have achieved through this 80 cell then is I have improved the I cell without impacting stability. Are you able to see this? Any questions? Ranjit?
Sir, when we are using mux greater than 1, then this is even an issue in the normal 60 SRAM cell, sir.
Yeah. 60 SRAM cell, so you anyway have to take care of stability. See, I started the discussion on this cell by saying, oh, read write are decoupled, so stability is no longer a concern.
Mm-hmm.
Now I am saying, no, stability remains to be a concern if my mux is greater than 1.
Okay, yes, sir.
Again, numerous papers in academia you will see who forget that there is a mux thing there. They simply say, oh, 80 cell is the panacea, it solves all problems. No, it doesn't. If you have mux greater than 1, it doesn't solve all the problems. You need to do something else.
Yes.
Many academic papers simply ignore that aspect. Okay, so I'm telling you this because I don't want you to fall into those traps.
Sir, can you once again explain this I cell concept that you told?
So, okay, in this particular cell, what determines the cell current?
The pull down in the read network.
Yeah, no, not just the pull down, the stack of the two NMOSes connecting RBL to ground.
Yes, sir.
See, when we were designing the similar stack on the regular 60 cell, we had to ensure that PG was much lesser than PD.
Yes, sir.
So my PG being lesser, even though I am giving area, my current was limited.
Yes.
Over here, I can have both the pass gate and the pull down large enough.
Yes, sir.
So in the same area, I don't need to have any constraint sizing on the pass gate, and therefore I can have more read current.
Yes, sir.
Are you able to see this?
Sir?
Yes, Raghav?
Sir, for example, when I'm reading in the bill, if I note if I have a 0 and I want to read that 0, so I put the read word line as 1. But then how exactly, but I'm not changing the word line to be 1. Then how I'm reading?
Yeah, so no discharge will happen. But if BLFI was 1, then RBL would have discharged. So you have read. See, if BLFI was 1, you take RWL to 1. What happens to RBL?
Oh, it discharges.
It discharges. If BLFI is equal to 0, what happens to RBL?
It doesn't discharge, sir.
So I have distinguished between 0 and 1. Na?
Okay. Right.
What does reading mean? I should be able to tell whether inside the cell there is a 0 or a 1.
Yes.
That I am able to distinguish on the RBL.
Yes. Yes.
Okay. So is there any new figure of merit that is introduced now? So we already have cell current, we already have stability, we have right margin. Is there anything else that you would want to consider as a designer?
So the mux part?
Mux was already there, but it is not a figure of merit of a memory cell, na?
Okay, yes sir.
Mux तो memory का feature है या memory का characteristic है.
So area?
Area was a figure of merit even for a 60 cell. That is not a new figure of merit here.
Yeah.
So,
Sir,
for example, so in this cell, since my reading and writing decoupled, so to improve my write, I can now increase the pass gate size.
Yeah. But as we just said, na, if mux is greater than 1, then you can't do it because of the stability constraints. You will still need to maintain the beta ratio for the other 3 unselected columns. है ना?
So, yeah, point.
The new figure of merit, is it the read speed?
Read speed or read current, we already had a figure of merit. Na? Cell current, we already had a figure of merit.
Okay.
But yeah, okay. The new figure of merit is also linked to cell current though. Okay. Now consider a case that you are writing. So you're using it as a dual port cell. You're using it as a one read write and one read memory. Do you see this cell can be used like that also? This is a read write port like a regular 60 cell, and this is a read only port. You cannot write through this port. Are you able to see this?
Yes sir.
So if I am using this as one read write, one read memory, then I could actually be writing on this word line and also reading from this port. Can it happen? I might be writing into this cell and reading this cell. So RWL is also selected and WL is also selected. Yes?
Sir, the lower NMOS of RBL is connected to VX, which is dependent on the write. So can we do it simultaneously, read and write?
Yeah, we can. There are 2 independent ports now. But that is where the new figure of merit comes into picture. If it so happens that this word line is selected, and let us say this was 0. So in that case, my bit RBL was not supposed to discharge. Are you with me? If BLFI was 0, and I selected both word line and a read word line, RBL was not supposed to discharge. है ना? Hello?
Yes sir.
Yes sir.
Now, if my word line is also selected, then this 0 goes to VX. So this NMOS turns partially on. So there can be some current it can sink. Are you able to see this?
So in this case, I'm trying to write 1 when there is 0, right?
No, I'm not trying to write a 1. I'm trying to write on some other cell. In the same row, some other cell I wanted to write there. This cell, I'm not doing anything. This cell only just turned on.
So why it turned on then?
Because the adjacent cell over here, there were 3 other cells now. I wanted to write on this particular cell.
Okay, sir.
Let us say. So the word line is common, it will turn on now.
Yes, sir.
So when the word line is on, then the 0 will go to VX.
Because bit line is BLB's VDD.
Charged to VDD, yes. Okay. So what happens as soon as it goes to VX, this NMOS turns partially on. So there is some new current that is now flowing. So until now, we were only looking at I on and I off. And I said that if it is I off, then this cell is storing a 0. If it is I on, then this cell is storing a 1. That was what I had distinguished till now. Now what we are saying is that there is also another current which is I partially on, which should also be considered as 0. Are you able to see this?
So this discharging from RPL when it goes to that is partially on.
Yes. Yes.
Okay.
So for that, sir, this lower NMOS, do we have to make it high VT NMOS or something else?
So if you make it a high VT NMOS, then what happens?
It will be sorry, not leakage. If we make it high VT, then it will take more time to turn on. Then the read operation will be.
See, if you make it high VT, then since this is VX, the IPON may go down a bit.
Yes, sir.
But then do you realize that ION will also reduce?
Yes, sir. Yes.
So you have to actually see. See, what you were looking at was, I want to distinguish initially between 0 and ION. Now we said, no, there is something which is IP on.
Yes, sir.
So, आप इतना सारा margin समझ रहे थे, that margin is not there. Actually, you have to have a sense amplifier which distinguishes between these two. Now you're telling me I will increase the VT of the device. So what could happen? This IP on could go here.
But still the margin is there.
But this could come here.
Okay. Yes, sir.
So my margin could actually reduce.
Yeah, yes, sir.
It may come only here also. I do not know. But it could come here also, na, potentially.
Yes, sir.
Depends on what voltage I am operating at. What is the sizing of these two devices? Depend on so many factors.
Yes, sir. Yes, sir.
So there is no single formula that it has to be HVT. Making it HVT may help. It may not help.
Yes, sir. Understood.
Additionally, you cannot simply make just one device HVT. अभी हमने layout देखा है SRAM cell का. If I make this HVT, this also needs to be made HVT. Otherwise, do you see there is a DRC between HVT and RVT devices? I cannot abut them.
Yes, sir.
So in an SRAM cell, you simply cannot say, oh, this device is low VT. You will see many academic papers simply doing this. Oh, I will just put one device at low VT. No impact on leakage. Arey bhai, if you do that, you cannot make the layout. You're not even considering the impact on area then. Okay?
Yeah, yes, sir.
So we design the cells very carefully. What is happening here? What is this?
Two read and two write.
Yeah. Two read write. Both the ports can do read write. So there would be a different cell which would be two read and two write. This is a two read write cell. Okay. Both ports can do read write operation. Then there are two ports. So this enables parallel access to the memory from two different processors. Can you think of the new figures of merit that will come into picture here? Hello? How will you measure the stability over here? What will be the worst case for stability? What will be the worst case for stability?
Word line 2 and word line 1 on at same time.
Yes, both the ports on at the same time. That is the worst case for stability. Is that also the worst case for read current?
So yeah, more current will flow.
What would be the worst case for write operation?
Both word line 1 and word line 2 are on with different values of BLs.
Yes. So we are saying that from one port, I'm simply keeping the precharge on. Okay, the precharge is on, but word line 2 is on. And other port I want to write. So what happens? Over here, there is a precharge that continuously supplies charge, which has to be sunk through the write driver. Till now, you are only designing write driver to discharge this node. Now your write driver has to sink this additional charge continuously. Are you able to see this? So this dual port memory cell is a little more complex to design than the single port memory cell. Design and analyze, primarily analyze. Design to ho jayega, but analyzing it is slightly more complex. You have to look at what are the worst cases and then qualify those worst cases. Are you able to see this?
So
yes.
What exactly was the worst case for the write?
Worst case for the write was that, see, there is a write driver over here. It was designed to sink this current only. But my other port also is on and the precharge of the bit line is on. So there is a VDD that is being supplied to this bit line, which goes from the first pass gate and now needs to be discharged through the write driver. So both word line 1 and word line 2 are on, and BL1 is equal to 0 through write driver, and BL2 is VDD through precharge.
Yes.
That would be the worst case for the write. There could be another worst case, which could be that, oh, my which you will realize when you will do that homework that I had given you last week, which could be that, let us say this word line 1 went on. Okay. And then word line 2 went on. And BL or BL1 discharged subsequently. So when one of the word line goes on, suppose there was a 0 stored here, what will it do? It will discharge this and it will discharge this also. Okay. Now you wanted to store a 1 here. Now the bit lines are discharged. The Vx was initially something, but it now falls because the bit lines have discharged. So it is Vx minus. When you will do the solve those equations of write analysis and read analysis, you will see that as the voltage of Vx reduces, what happens? As the voltage of Vx reduces, the writability of the cell would degrade. So that could also be another worst case. This is slightly more complex. You need not bother about it, but I just want you to remain open to other worst cases that could be there in this particular cell because of two ports. Two ports which are asynchronous. One port could turn on before the other port. Okay.
So ideally, when I have two ports, I want to access different bit cells using these ports. Or
yeah, I am accessing different bit cells only, Raghav.
Okay.
Just the adjacent ones.
Yes, sir.
For one, I am addressing address 0, and with the other port, I am addressing address 1. Because it is mux 4, they are appearing in the same row.
Yes, sir.
Is this clear? Great. So this is about the SRAM cells. I was hoping that we would also cover ROM cells today, but we will now pick them up in the next class. In the next class, please also come prepared with the homework that I had given in the last class. Please do attempt that. Otherwise, what is happening will simply go over your head. Okay. All the best. Thank you, guys.
Hello, sir.
Yes.
Can you repeat the homework question, sir?
It's there in the recording. It's also there in the slides. They're uploaded on the. Huh? ठीक है ना? Yeah.
Sir,
yes.
Sir, in the first memory cell that you just showed, so there was a little bit like mux exactly what the stability it was posing. Actually, it was little bit confusing to me. I mean, when you introduced mux, because you said that key apparently it saw me that the stability would increase, but with mux you said it degraded.
Yeah. So just look at the recording again. You will see. Okay.
And sir, there was also one question, sir. Like when we were doing the cell optimization, there was like key with the small PD, the writability would improve. But like so when I'm talking about the writability, I'm focusing on the zero, key how efficiently. So why I'm considering PD then basically that small PD would improve the writability.
Solve the homework that I gave you. You will see VX has a very important role to play. If PD is small, VX would be high.
Yes, sir. Okay, that has an impact. Okay. Okay, sir.
Okay. Chali. All the best.